I welcome you all in this lecture on Bode Plot. Bode Plot is a method of studying the frequency response of a system, and that is basically the response of a dynamic system when it is subjected to a sinusoidal input. Okay. So, the frequency response as we can talk about is that if we plot a set of values of the magnitude say g j omega and a phase angle phi that occurs when a sinusoidal input signal is varied over a range of frequencies. So, when sinusoidal input signal is varied over a range of frequencies, then if we plot the magnitude of magnitude and the phase angle, so this is what is termed as the frequency response. Now, this frequency response can be represented with the help of two graphs, and these graphs are, the first is the magnitude versus angular frequency, because here we are interested in varying the frequency and seeing the variation of the magnitude, and the second one is the phase angle versus angular frequency. So, by varying the phase angular frequency, we are interested in seeing the variation of the phase angle. So, these magnitude and angular frequency are plotted using logarithmic scale, okay, and such a plot is called the Bode plot, okay. And in this Bode plot, magnitude is expressed in decibel units, and this is how the expression for the decibel unit is, that is g j omega magnitude in decibel is equal to 20 log on the base 10 g j omega magnitude, okay. So, this is how it is expressed. Now, let us take example of Bode plot. So, first we will be taking an example for a system having a transfer function, say Gs is equal to k, where k is a constant, okay. So, the transfer function Gs is equal to k is here, and here the k is constant. Now, I can get the frequency response function from this transfer function by replacing s by j omega, okay. So, I get g j omega is equal to k, because I get the same thing, because here k is a constant, okay. So, what will be the magnitude of g j omega? This magnitude will be actually under root x square plus y square, okay, where x and y are the real and imaginary component of g j omega, okay. So, here the real component is k and imaginary component is 0. So, here this will be k only, okay. So, this magnitude is k, okay, and if I write it in terms of decibel, this is 20 log 10 k, fine, and the phase angle here is going to be 0, because tan phi is actually y by x and the y component here is 0. So, your phase angle is going to be 0, okay. So, if we see see the variation of the magnitude and phase angle with angular frequency, then here you can see that the magnitude variation with omega, okay, and this is what we are plotting, that is 20 log k. So, 20 log, this is on base 10. So, 20 log k, and you can see that this is a constant, okay, whereas the phase angle is 0, okay. And so, here we are plotting for omega is equal to say 0.1, 1, 10 and 100, that is these are numbers are multiple of 10, okay. So, this is what how the Bode plot looks like for a transfer function Gs is equal to k. Now, let us look at Bode plot for a system having transfer function Gs is equal to say 1 by s. Okay. So, again we can get the frequency response function for Gs is equal to 1 by s by replacing s by j omega. So, g j omega is 1 by j omega. Okay. I am replacing this s with j omega. So, this g j omega I can write as minus j by omega. This is how we get because our g j omega is 1 by j omega. So, to express it in terms of the coefficient of j, what is done is that we multiply the numerator and denominator by j. So, here this is j by j square omega and this j square is minus 1. So, this is minus j by omega. So, this is what we get minus j by omega. Now, the magnitude of it is equal to what you see g j omega is expressed as x plus say I y or x plus j y. So, here the magnitude of g j omega is given as under root x square plus y square. So, in this case this will be under root 1 by omega square or this is 1 by omega. Okay. So, this is what is the magnitude is 1 by omega, and in decibel this magnitude can be written as 20 log 10 1 by omega, and this is basically 20 log 1 minus 20 log omega, and log 1 is 0. So, what we have finally is minus 20 log omega. Okay. So, we can see this is the magnitude in decibel, and now if I plot it magnitude in decibel, then you can see that when I put the omega value as 1, this is what I am going to get, that is 0. So, the magnitude is 0 corresponding to omega is equal to 1. Similarly, if I put omega is equal to 0.1, this magnitude from here is going to be 20, and similarly I can plot this for the other value of magnitudes of omega. Now, coming back to the phase angle phi, we know tan phi is y by x. From here tan phi will be y by x, and so y here is 1 by minus 1 by omega, y component from here, and x component is 0. So, from here we get phi is equal to minus 90 degree. Okay. So, I can plot the phase here that is variation for it with omega as constant, and that equal to minus 90 degree. Okay. Now, next let us see the Bode plot for the first order system. Okay. So, let us assume the system have got a transfer function Gs is equal to 1 by tau s plus 1, where tau is the time constant. Okay. We get the frequency response function from this transfer function by replacing s by j omega. So, g j omega is equal to 1 by j omega tau plus 1. Now, I can represent it in the conventional complex number representation of x plus j y, I multiply the numerator and denominator by 1 minus j omega tau. Okay. So, this is what I get. Okay. So, 1 minus j omega tau in the numerator, and the denominator I will be getting 1 plus omega square tau square. So, 1 plus omega square tau square in the denominator. So, this is what I am going to get. Okay. So, we have this portion is actually the x component and this portion is the y component. So, I can find out the magnitude here is equal to under root x square plus y square, and if I do that, this is what I get 1 by under root 1 plus tau square omega square. Now, I can write this magnitude in decibel as 20 log 10 1 by under root 1 plus tau square omega square. So, this magnitude is magnitude in decibel is this 20 log 10 1 by under root 1 plus tau square omega square. Okay. Now, we can see that when omega tau this is very much less than 1, or omega is very much less than 1 by tau, then what happens? I can neglect this value because it is very much less than as compared to 1. So, this whole value becomes 1. Okay. So, what we get magnitude in dB as 0. So, omega tau or tau omega very much less than 1 by tau, this is what value of magnitude we get, that value is equal to 0. Okay. Now, there can be another case when omega tau is very much greater than 1, or say omega is very much greater than 1 by tau, then in that case this value will be basically I can neglect this one in that case. So, what I will have is 1 by root of tau square omega square, or 1 by it will be tau omega. So, I have got 1 by tau omega, or which I can write as minus 20 log 10 tau omega. Okay. So, this is what I can write. So, if I plot this, okay, then this is what I am going to get. So, this is the straight line approximation for plot of this portion, and this is the plot for this portion. Okay. And you can see that the intersection of these two straight line, what we call as the break point or the corner frequency. So, this is what it is called. Now, next let us look at the frequency response function. As I was telling you, we had this value of the frequency response function, and this value is my x value and this value is my y value. Okay. So, the phase of the first order system, from here I can write the phase tan phi is equal to y by x. So, this is my y component with a minus sign, and this is my x component. So, what I get is minus omega tau. Okay. Now, you can see that at low frequencies, say omega less than 0.1 by tau, this value is going to be very near to 0. So, tan phi is equal to 0. So, we have the phi is equal to 0. Okay. So, if I plot this phase with omega, say omega less than 0.1 by tau up to here, this value is almost 0. Okay. Similarly, at higher frequencies, that is say omega greater than 10 by tau, okay, or omega tau greater than 10, this phi value will be equal to minus 90 degree. Okay. So, here you can see that omega value greater than 10 by tau, this value is going to be equal to minus 90 degree, and between these two frequencies phase can be approximated as a straight line. So, this way we can draw the Bode plot for the first order system. Now, let us see Bode plot for a second order system. Okay. So, if we have a second order system, say with the transfer function Gs is equal to omega n square by s square plus 2 zeta omega ns plus omega n square. Now, the frequency domain response function can be given for this second order system by replacing s by j omega. Okay. So, if I do that, I replace s by j omega, this is what I get, g j omega is equal to omega n square by here j omega square plus 2 zeta omega n into in place of s, it will be j omega plus omega n square. okay, or here I can write this as omega n square. Here it will be actually j square omega square, and j square is minus 1. So, we have minus omega square plus 2 zeta omega n j omega plus omega n square, okay. And again I can write in the conventional form of x plus j y by multiplying numerator and denominator by say omega n square minus omega square minus 2 zeta omega n j omega in the numerator and similarly in the denominator. So, if I do that, this is what I get g j omega as 1 minus omega by omega n square minus j 2 zeta omega by omega n, okay, and this is what the denominator which I am going to have. So, this is my g j omega value. Now, if I am asked to find out the magnitude for this, again the magnitude will be given by under root x square plus y square. So, if I do that, that is what is x, x component will be this divided by the whole, and similarly the y component will be this one divided by the whole, okay. So, if I do this, this is what I am going to get 1 by under root 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square here, okay. So, this is there. Thus, in dB this magnitude can be written as minus 20 log 10 under root this whole factor, that is 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square. Now, let us see the behavior for this, that is the plot of this magnitude with omega by omega n. So, here we have in x axis omega by omega n and in y axis magnitude is there plotted. Now, here you can see that for omega by omega n very much less than 1. So, if this value is very much less than 1, I can neglect this, I can neglect this. So, what remains with me is 1, and that is log 1 is going to be 0. So, this is what I am going to get this line, okay, when omega by omega n is very much less than 1. Similarly, for if your omega by omega n is very much greater than 1, then magnitude approximates to minus 20 log 10 omega by omega n square, okay. So, this is what we are going to have, because in that case I can neglect this term, I can neglect this one, okay. So, this is what I am going to have minus 20 log 10 and omega by omega n square, okay. So, this is what I am going to have. Now, this intersection of this one and this one actually gives us a straight line, approximate straight line, okay, and this both the intersection actually will give you the break point. Now, the true value actually, the true value here depends on what the damping ratios are here, okay. So, for the different damping ratio this has been plotted. So, this was our g j omega function, okay, and in this case the phase, coming to the phase, this phase is given by tan phi is equal to y by x. So, this portion is y with a minus sign divided by x is this one. Now, if I am interested in plotting say the phase with omega by omega n. So, let us say that initially omega by omega n is very less than 1, say 0.2, and in this case if this is very much less than 1, I can neglect this, okay, and so this is going to be approximately very small. So, phi value I can take as 0. So, here for omega by omega n less than 1, you have this value almost 0. and if this omega by omega n is very much greater than 1, okay, then say this value is phi, and so this value is since going to be high, we can take phi tan phi is infinity, and so phi is equal to 180, okay, and so this value will be 180, and when omega is equal to omega n, this value becomes infinity, and so phi is equal to minus 90 degree. Okay. So, here you can say this value corresponds to phi is equal to minus 90 degree. Now, when we are building up a Bode plot, okay, we can do so for a system which is composed of many subsystems, okay, and say we have a system that has got transfer function Gs is equal to G1s, G2s, G3s and so on. So, the frequency response function for a 2 element system will be given by, I can replace this S by say G j omega is equal to, this is G1 j omega into G2 j omega. Now, this G1 j omega I can write as magnitude of G1 j omega into cos phi 1 plus j sin phi 1, where phi 1 is the phase angle. Similarly, I can write G2 j omega as G2 j omega into cos phi 2 plus j sin phi 2, where this phi 2 is the phase angle. So, the product of these two G1 j omega and G2 j omega is given by this, and we can substitute these two expression back here. So, the for G1 j omega I have G1 j omega cos phi 1 plus j sin phi 1, and for G2 j omega it is G2 j omega magnitude into cos phi 2 plus j sin phi 2. So, this G j omega is this one, the two magnitudes we can keep together, and here are the cos phi 1 plus j sin phi 1 into cos phi 2 plus j sin phi 2. Okay. So, now if I split up this bracket, so what I will be getting cos phi 1 into cos phi 2, and what I will have is here when I will multiply this with this one. So, I will have minus sin phi 1 sin phi 2, which will be basically cos phi 1 plus phi 2. Likewise, I will have the multiplication of cos phi 1 with sin phi 2 and cos phi 2 with j sin phi 1 will be giving me j sin phi 1 plus phi 2. Okay. So, for Bode plot, this is our the combined magnitude. So, in the log scale I can take this log 10 G j omega, and since these are the product, its logarithmic is going to be sum. So, we have log 10 magnitude of G1 j omega plus log 10 magnitude of G2 j omega. So, for this type of system we can just add the Bode plot for the individual subsystems in order to get the Bode plot for the whole system. So, let us see an example of building up a Bode diagram. So, the Bode plot of Gs is equal to 10 by 2s plus 1 if I want to do, okay. I can basically see here that I can split up this whole transfer function into two transfer function, that is two transfer function for two subsystems, one given by G1s is equal to 10 and the other given by G2s is equal to 1 by 2s plus 1. So, this is very much similar to what we have seen that of G s is equal to k, and this is what we have seen in the previous slides of Gs is equal to 1 by tau s plus 1. Okay. So, I can replace this S by j omega, and then I can draw the Bode plot. So, for the first one you can see that this is a constant. So, for the 10 this portion is going to be the Bode plot for the first one, and similarly for the second one, this is the Bode plot 1 by 2s plus 1, and as I have shown you in the previous slide, for the combined that is transfer function G1s into G2s, we can get the Bode plot by simply adding up those. So, I add up this with this one, so this is what I get. So, this represents the magnitude in the Bode plot for the transfer function 10 by 2s plus 1. Similarly, for the phase in case of the first one, okay, we had phase as 0, and for the second one this is the phase, okay, and for the combined one we will be having this that is the darkened one as the phase one, okay. So, for higher values this becomes minus 90 degree, lower value this is 0, and in between value is given as a straight line, and this and 0 summed up will be giving you the same thing. Now, coming to the performance specification, okay. So, if we want to indicate the performance of the system, there are two parameters with the help of which we can indicate the performance for the frequency response, okay, and these are the peak resonance and the bandwidth, okay. The peak resonance basically is the maximum value of the magnitude. So, as you can see that in this plot we are plotting the magnitude in decibel with respect to omega, and say this is the system response. So, here the peak value is actually the peak resonance is the maximum value of the magnitude, that is what is called the peak resonance, and the bandwidth is basically defined as the frequency band between which the magnitude does not fall below minus 3 dB. So, say if this is our 0 value here. So, say after this the magnitude falls below 3 dB minus 3 dB, then this is going to be the bandwidth for the system. So, with the help of these two parameters, that is the peak resonance and the bandwidth, we can specify the performance of the system, okay. So, this is what I wanted to tell you in this subtopic. For further reading, you can refer a very nice book by Professor Bolton, that is Mechatronics by Pearson Education. Thank you.